Hello everyone, welcome back to my YouTube channel. I hope you all are doing well and good. The subject I am going to be taking over today is going to be ATC, that is Automata Theory and Compilation Design, bearing the subject code 21 CS51. So, without any delay, let us get into the topics. The following topics are going to be delivered in this particular video. First one being the introduction to DFA, followed by components of DFA, the accepting states, the formal definition, the differences between DFA versus the NFA, the applications of DFA, and finally we have the conclusion. So, moving on to the first slide, we have introduction. A deterministic finite automata is a mathematical model of computation and a type of finite automaton. It is a specified abstraction of how a computer or a machine might actually behave when processing a further input, or it may even be defined as follows. DFA is a finite automata in which for each and every input symbol there is exactly one transition out of each and every state. So, moving on to the next slide, we have the components of DFA. The components of DFA are as follows. At first we have the states. In a deterministic finite automaton, the set of states represents the various configurations or conditions the automaton can be in during its computation. The set of the states is denoted by Q and it is specific as well as finite. Each state in Q signifies a specific point in the computation process. Nextly, we have the alphabet. A symbol is an abstract entity. Letters and digits are examples of frequently used symbols, and an alphabet is a finite, non-empty set of symbols, and it is denoted by the following symbol. The example is going to be 0 and 1, which is governed by curly parenthesis, or it can even be ABC. In this case, that is also governed by curly parenthesis. Moving on to the next slide, we have the transition function. The transition function in a deterministic finite automata specifies how the automaton actually transitions from one state to another based on the input symbols. The transition function itself is denoted as delta and plays a very crucial role in defining the behavior of the DFA. Moving on to the next slide, we have the accepting states. In a deterministic finite automaton, the accepting states are also known as the final states and are designated states in which the automaton is going to accept a particular input. When the DFA reaches an accepting state after processing the entire input string, it is going to signify that the input string is recognized or accepted by the automaton. The key points relating to accepting states are as follows. Firstly, we have the designation as an accepting state. Certain states in this set of states Q are marked as the accepting states. The set of accepting states is denoted as a subset and F subset Q, where F is going to represent the set of all the accepting states. Moving on to the next slide. Acceptance of input. If the DFA, after processing the entire input string, lands in one of the accepting states, the input string is considered accepted by the automaton. The acceptance criterion helps defining the language recognized by the DFA, which consists of all the input strings that lead to the accepting states. Next, we have the rejection of input. If the DFA, after processing the entire input, does not reach any accepting state, the input string is considered rejected. And the last point being representation in transition state. In the transition table of the DFA, the accepting states are often indicated in some way. Here the example would either be a shading or a special symbol to distinguish them from the non-accepting states. So, moving on to the next slide, we have a formal definition. So here remember that the DFA itself is a phi tuple or a quintuple, and I am going to be representing this tuple with the letter M. So here M is going to be consisting of Q, sigma, delta, Q naught and F, wherein Q is a non-empty finite set of states, sigma is a non-empty finite set of input alphabets, delta is a transition function, Q naught that belongs to Q is a start state or rather also termed as the initial state, and we have F that is also a set of accepting or rather the final state in this case. Moving on to the next slide, we have the differences between DFA versus NFA. First I'll cover DFA, then followed by NFA. So, as we know, DFA stands for Deterministic Finite Automata, and for each and every symbolic representation of the alphabet, there is only one state transition in DFA, followed by which DFA cannot use empty state transitions. DFA cannot be understood as one whole machine. In DFA, the next possible state is distinctly set, and in DFA, it is way more difficult in order to construct because the number of initial states are set and the transitions are also going to be one per state. Time needed for executing an input is also less. Finally, we have DFA rejects the string in case it terminates in a state that is different from the accepting state. Nextly, we have NFA. NFA stands for non-deterministic finite automata. There is no need to specify how does the NFA react according to some symbols. And NFA can also be used for empty string transitions, followed by which NFA can be understood as multiple little machines computing at the same time. NFA is easier to construct. Time needed for executing an input string is more. And lastly, we have NFA rejects the string in the event of all the branches dying or even refusing the string. Hope you understood this slide well. Moving on to the next slide, we have applications of DFA. Lexical analysis in compilers. DFAs are extensively used in lexical analysis phases of compilers. Lexical analyzers, are also known as scanners, are going to be useful for the DFA in order to recognize and even tokenize the input source codes into meaningful units, such as keywords, identifiers, and operators. Pattern matching algorithm. DFAs itself are going to play a very crucial role in pattern matching algorithms. They are useful to search for specific pattern within a given text or sequence of characters. Regular expressions, which are often used in string matching, can be converted into DFAs for efficient pattern matching. Nextly, we have network protocol analysis. DFAs are employed in the analysis of network protocol, and they can be used to model the behavior of network protocols and to verify whether a given sequence of messages conform to the expected protocol specifications. Moving on to the next slide, we have syntax analysis in NLP. DFAs are utilized in syntax analysis of natural languages, and they can be used to model and reorganize the syntactic structure of sentences, helping in tasks such as parts of speech tagging and parsing. Validation of input in software application. DFAs are applied to validate and recognize the input strings in software applications. For example, they can also be used to enforce rules for validating email addresses, passwords, or other user inputs. Finite state machines in hardware design. DFAs are used in hardware design to model and implement finite state machines and are essential components in digital circuit design and controls. String matching algorithms. So algorithms for searching and matching strings are often leveraged for DFAs. The construction of a DFA from a pattern allows for efficient string matching, such as in the Boyer-Morse algorithm. Finally, we have the conclusion. So remember that in conclusion, deterministic finite automata serves as a fundamental tool in computer science and various applications. Their deterministic nature and simplicity makes them valuable for tasks such as lexical analysis in compilers, pattern matching algorithm, network protocol analysis, and syntax analysis. DFA actually finds a practical use in validating input in software applications, implementing finite state machines in hardware design, and enhancing security measure through intrusion detection. With the applications ranging from text editing to robotics, DFAs actually provide a structured and efficient way to model and recognize patterns and behaviors, contributing significantly to the field of formal language theory and automata theory. So, I hope that whatever topics were actually covered in this video were understood well and good, and I hope that you understood the key differences between DFA and the NFA. Thank you for watching the video.